We did these interlocking pictures, and it's sort of the interlocking, you can think of as sort of recursive elements. These are interlocking together. So the picture language isn't exactly Escher, but it's something like it. So what we can do in the picture language is we can take a picture, say, happy little stick man. Were this an actual lecture, you would be seeing Philip and Alex right now. And we can do things like do a split of it where you get happy little stick man. And more than that, we can do more complicated patterns where we would get happy little stick man, who would get fatter up here in these windows. That would split this way here.
By the way, who is Peter Henderson? Was he a student at MIT or something?
No, he was a researcher, I believe, at the University of Oxford. And he was at Oxford when he did this. And then we could have happy little stick man.
Is this a student thing, or this is?
So let me just draw a happy little stick man, then we'll talk about happy little stick man. Okay, so there's happy little stick man. Okay, so the picture language is implemented in Scheme. However, it is not part of basic Scheme. Okay, so it's a package that's written on top of Scheme for us to use for this problem set. In our picture language, the basic element, our primitive, is called a painter. This is a painter. This is a painter. This is a painter. Painters, like cons, have the property of closure. So if we operate on a painter or more than one painter, it returns a painter. So that we can do neat little recursive things with painters, like split them out this way. Okay. A painter, you could think of as a picture, but it's actually a procedure. And it's a procedure that takes a frame. A frame is the window that we want to display the painter in. So you briefly saw two windows up there on the screen. Had it actually worked, you would have seen the painter pop up in that window. Now when we talk about frames, there's two things. Let's say you have your graphics window, which will be labeled G1, G2, or G3 when you guys are running this problem set. So this is a frame. And this is the frame that we want to display the painter in. There's three things that describe this frame. There are three vectors. One is going to be a vector from 0, 0 in screen coordinates. Your computer needs to know how to draw things up on the screen, and it uses X and Y coordinates to be able to do this. Okay, so there's some 0, 0 on the monitor that's defined. It may be the lower left corner, maybe the upper right, maybe the center, we don't know. But there's some origin on the screen. So we have a vector pointing to the origin of our frame. We'll call this vector origin. There are two more vectors that we need to specify a frame. The first one is edge 1, and the second is edge 2. So this specifies the window in which we want to display our painter. So if we pass the window G1 to our painter, then our painter will be displayed in this frame. Well, of course, it's not quite that simple, is it? What we need to do is our frame may not actually just be this window. Our frame may be some portion of that window. We may need to scale our image. So to do scaling, what we do is we convert the frame we convert our picture into frame coordinates. Frame coordinate map. So each frame is mapped into a unit square. So we take a unit square, and this is what's going to allow us to display our picture in any size frame that we're trying to use. And the way that we compute is given some vector xy, the point is going to be, just actually write this down. The origin of the frame plus x times edge 1 of the frame plus y times edge 2 of the frame.
What was the v vector, vxy?
The v vector is just some point in our image.
Okay.
So basically what we're going to do is we're going to go over our image in frame coordinates. In the xy coordinates, we're going to map it. Rather, the xy, sorry, is in the unit box coordinates. So we're going to have our frame in that, and this is how we map it into the window. So we take this xy here. Let's say at this point it would be 0.5, 0.5. So we take the origin of the frame, which is this origin vector here, the frame's origin. So let's say that was 100, 100. And then this would be 200, 100. This up here would be 100.
Pixels or?
Right. They're in screen coordinates, so it would be pixels on the screen. So if we wanted to convert this here, 0.55, over into drawing it in this window, it would be the origin of the frame.
The origin vector?
Yeah, right. So the 100, 100, plus the x, 0.5 of the edge 1 vector, plus 0.5 of the edge 2 vector.
No. It's the difference between the edge 1 vector and the origin on the left-hand corner. You're giving me, for 200, 100, you're giving me the distance from the original origin. You want the coordinates from the new origin, 100, 100 to 200.
The edge 1 should be a horizontal line.
Edge 1 is
Right, so this is going to give me
100, 0. 100, 0.
there's 200, yeah. Yeah. Right, but it means that the book is telling us the wrong thing. So, okay, so we're going to get times that edge vector. So if we do the difference, it's which would give me which would give me 150, 150. So, in that very confused way, we find how this 0.5, 0.5 is going to map into this point here.
The edge of the frame coordinates, or just the x coordinates?
So it's going to actually compute the difference between this point and the origin to give us that edge vector. Okay, so this is lots of grungy internals. Let's talk a little bit about what we would want to do. Let's say I want to write a procedure. And I'm going to call this procedure right split. And what right split is going to be defined to be is in this image, we're going to have the identity, or the picture that it's passed. And here we'll have the right split on n minus 1 and the right split of n minus 1. So right split takes two things. It takes a painter, and it takes some number for our recursion. Okay, so in fact, if we had more, if our number were 2, what we would get is this. Okay, so we're going to be recursing where this section may either turn out to be the identity or the painter, or it may turn out to be a recursive call. So let me tell you that we have two procedures defined for us. One is called below, which takes two painters, painter 1 and painter 2. And what it returns is painter 1 painted below painter 2. We have another procedure called beside, which also takes two painters. And what it returns is painter 1 next to painter 2. Okay. Given that we have below and beside, how could we think about writing right split? Let's not actually write code. Let's actually just talk about how we might do this. So what's this picture? What's on the left? What's on the right? Well, if I'm asking what's on the left, what's on the right, we're probably going to do what procedure to put those two things together? Beside. So we're going to have some beside of this thing and that thing. Okay, so we will call that squiggle 1 and squiggle 2 to be formal. So what is squiggle 1? It's just going to be the painter. So this is just going to be the painter. Okay, good. What's this going to be? It's going to be a call to below of what we could call affectionately squiggle 3 and squiggle 4. Okay, so this would be squiggle 3. What is that? How do we define, what did I write here? This is the right split on n minus 1. So this is a recursive call to right split.
I thought that below, put the first call below.
Yeah, sorry. This would be squiggle 3. Okay, so what is this? Well, this is a recursive call to the procedure. Okay, so we're going to have a call to right split on the painter minus n1. Similarly, a right split on the painter minus n1. Again, sort of pseudocode-ish, right? None of this is actually working. It's just talking about what we're going to do to write this procedure. Okay, I'm putting two calls, two exact same calls that are creating painters. They're creating the same painters below each other. Now, we've talked a little bit about let. Would this be a good place to use let? Sure, because then we wouldn't need to compute this and then compute this. We could compute it once. So rather than branching out and having to do this twice, if I were to write it this way, what would be my order of growth in time? Is it n squared? If we branch out, 2n, right? Every step we're going to do 2 more recursive calls. You can think of this as towers of Hanoi, right? So we started off with the tower of 4, and we had to call to move the tower of 3, the tower of 3. then for the 3, we did a tower of 2, tower of 2. Okay, so this is a bad way to write code. It's going to take a really long time. So we'll use a let. So let's define our right split procedure. I'm going to define right split, which is going to take 2 arguments. The first being a painter, which, remember, is a procedure that when given a frame will draw some picture up on the screen. And the second thing is going to be our number for recursion. Okay, now, what is going to be our base case? Well, otherwise we want to do this, right? We want to put the picture beside this with the below of those 2 things. And we just said we want to use a let. So this is where we're going to put our let. I'm going to let my smaller image be right split on my painter, subtract 1 from num. Now that I've computed that smaller, I can say beside painter, below smaller, smaller. Questions? Yes? No?
Oh, I'm just trying to
Okay.
look at what that second, that last statement
So this last statement is doing what this pseudocode stuff was saying over here. We have to put 2 things beside one another. This thing and this thing. But the second thing that we're passing to beside is actually 2 pictures on top of one another. So that's the below on the smaller and the smaller. And the reason we did that call was to prevent us from having to calculate this twice. That's why we use the let. Okay. So how would we define something called corner split, where this is the identity, this is an up split on n minus 1, this is an up split on n minus 1, this is a right split on n minus 1, right split on n minus 1, and this would be a corner split of n minus 1. So how would we define this? Corner split is what we're currently defining. So corner split is going to take, just like right split did, a painter and some num, and then return this image. Up split, I'm not going to actually define for you guys here. It's one of the exercises in the problem set. Okay, but an up split would return this. It's very similar to right split. Okay, so you guys will write that in the problem set. That'll be you guys writing up split. But right now, since we're on the board, let's just assume that we have up split written. Okay, so given that we have up split, let's talk about how we would write corner split. Anybody want to?
We're going to have a beside, and then inside that will be below.
All right, so we're going to have a beside, a below,
Identity, and then another beside. Up split.
Okay, so that takes care of that. So how would we write this one here?
Below. Below.
And that comes below a recursive call to corner split. Okay.
Can you walk through that real briefly?
Sure. What we're doing is we're just pasting painters together, right? So what we can do is we can look at this and say, well, what I need to do is I need to paste a bunch of stuff together. So the first decision we made was to look at these two halves, one half here, one half here. If we can get those two halves, we can use a beside to paste them together. Okay? So that's our first beside here. So now that we're just pasting these two halves together, we have to figure out how to get these two halves. Well, if we look at this half, we can say, well, that's the identity below this thing. Okay, so that's the below ident. And then we need to figure out how to get this thing. Well, that's a beside of an upsplit, upsplit. Similarly, on this side, for our second half that we said these are the two things we need, we can use a below to get this chunk below that chunk. Well, what's this chunk? Well, this chunk is another below of a right split, but beneath another right split. And that is below our recursive call to corner split. Okay, we could have said, instead of breaking it immediately into two besides, we could have just broken it into two for below, right? We could have gone the other direction, right? I just broke it that way. We could have started off this way. Does it matter?
Well, yes, it does, because we need to do our upsplit off our identity, doesn't it?
No, okay, so we're just calling any of these procedures with the painter, right? So it doesn't really matter if we were to do it one way or the other way. But because we did the last one as two besides, I thought it would be easier if we started off as a
That's
beside.
what I'm curious. There isn't a frame of reference that you have to start from necessarily. Like there's not one procedure or one frame of those 2, 4, 6 that kind of is your base, and then you build from that. You can just kind of break it up in any way you see makes sense to you.
Well, I mean, so there is some natural breaking up, right? Because our identity is down here on the left, and our recursive call is up here on the right. But the actual pasting together can come in any order that we want, as within reason, right? I mean, because below takes two things. So to put two objects below each other, you wouldn't want to try to combine somehow up and right. Right? There's some sort of natural way using below or beside that you would use to combine these. But certainly it doesn't matter if we try to do basically below of this piece and that piece, or whether we do a beside of this piece and that piece. Okay. So given that recursive idea, let's write the code. Okay. So define. Oh, by the way, if you guys, this code should be in hand.scheme, which is the handout that I gave you guys. You should see this code. So we're going to define corner split on a painter and a num. Same thing as last time. If our number is 0, return the painter. Okay. So, what might we want to use a let for? What do we not want to calculate a couple of times? Right, the right splits and the up splits. So let, I believe it's called up. Up be a call to up split with the painter on num minus 1. Okay, so that's computed these two up splits. And then let's compute right. That's going to be a right split of a painter minus num 1. Right. So now we've got the up split and the right split. So we're going to have another let nested underneath this one. And this is just to make the code a little bit easier to read at the bottom level. And we're going to define the top left to be a beside of what two things? The top left corner. Right, so we're going to beside up, up. And then we're going to have bottom right, which is going to be what? A below right, right. And finally, we'll have, I guess this is called, let's call it corner. And what's corner going to be? What's this upper corner going to be? A recursive call to corner split. Corner split called with the painter and num minus 1. 4. Right? 1, 2, 3, 4. Okay, so now that we've got all these locally scoped variables, what do I now want to do? What we've got here, right? Substituting in the variables that we defined using our lets. So we're going to have a beside of what? Beside, below, identity, which is in this case the painter. Top left. Remember that we had declared beside up up as a temporary variable in this let up here, so we can just use top left. With a below of, well, what's below right split, right split? That's our bottom right here. And the corner. Two. Let, if, define. They're all there.
Exponential notation.
Well, that is. See, they kind of go up. So I could just do paren to the end.
If you define the
See what we want. Let me show you. So the question was, could we scope that? And if I had the computer, I could show you what it was actually doing. But here, let me try to draw it. So what the corner is doing is, let's say that we call a corner split on 2. Nice small number. Whack. So here's going to be happy little stick man. Now this is going to be an up split of 1. So we get happy little stick man here, like that. So we do actually need to recalculate because we need that recursive call. Right, because as drawn here, it looks like we're just going to keep using the same thing. But we need to have that recursive call to up split there. Similarly with right split here. Here's happy little stick man. which I suppose in some examples I should make happy little stick woman. To be gender equal. There we go. So here's happy little stick woman on a bad hair day. So then this is the corner split of n minus 1. Well, what's the corner split of that? And then this is going to be the up split of n minus 1, which is 0, which returns the identity. Okay, so that's what the corner split's going to look like.
Actually, it's going to do it once more, right?
So this is with 2, so this was called with 1. And then, so this is going to call this on 0, 0, 0. So no, it would return the identities at that point. So this was the corner split.
If that's the corner split of n equals 2,
2.
then that would be the corner split of n equals 1, right? So you'd still up split 1 and right split 1.
No, but no. Remember, we call the up split and the right split on n minus 1. Right? So this is going to be, this chunk here is the corner split of 1, which means that this chunk is the up split of 0. And this chunk is the right split of 0. And this chunk is the corner split of 0. Okay?
So if there's 3, then the corner split would start to have.
But that's not the picture that you originally drew.
It is, in fact, the picture I originally drew, because all I said is that this is a recursive call to up split n minus 1. I didn't draw up split of n minus 1, but I said it was going to be up split of n minus 1.
Corner split here is a different picture than what you have.
Well, okay, so corner split here was assuming that this is larger than 0. If this were, rather, it was a corner split of more than 1. If it was a corner split of 1 that we called, it would look like that. If you guys want to see, we could do a bigger case, thus avoiding drawing hair. Yes, we get a bald woman too. There you go. We're all living in gender neutral land. Okay, so here's 4. So this means this has to be an up split of 3, which means this is an up split of 2, which makes this an up split of 1, and these are zeros, which is what I had before, but somehow it makes more sense to me with the little guys. Okay.
In your first call, you're not splitting.
Excuse me? In the first column, not what?
First call, you're not.
Remember that we had up split, which unfortunately has been erased. Actually, up split hasn't been defined.
What you've drawn there, wouldn't that be doing the right split on the top? Because you're splitting it for the.
No, it's an up split. Oh, but I'm sorry, I skipped, I didn't do, yeah. Do-do-do-do-do. Even confused with happy little sick person. Whack. There we go. This is 3. And then this is 2. These are 1. And etc. Oops. This one. See, I was really expecting to have that little projector behind me at this point. So, we could do it this way. Anyways, hopefully you guys are getting the idea. Okay. So that's how it goes out. So that's the up split. The right split is going to do it. Right split, chunk. This. Yeah, etc. Out that way. And the corner split will be the recursive call. So we'll end up getting with, anyways, let's go to the lab and you guys can type this in and it'll work and you'll see what it looks like.
I still don't understand why this corner split is the box with 4. Why is that the square with the 4 boxes? I still think it would look different.
I do too.
The picture on corner split does show the little people, as you're showing your right most recent diagram, show the little people coming over to the little upper right corner, which is different. See, in your first picture, the corner split upper rightmost stick man is bigger than his left siblings, and that's not the way the photograph comes out of Rogers.
Which is probably
and as
correct.
explained by that, there's one more depth of call to. There has to be a call to upsplit and right split.
Right,
See
within
how
that,
little-
yeah,
so
yes.
we get little, the way they show.
Right, so I goofed here.
Okay, not too big.
Why don't we just do this at the lab?
Yeah. I'm just not a good scheme interpreter. Anyways, it's fine. Go ahead. Obviously, they would be all the same. Because what's happening is each of these painters is given a particular frame to reference where it's going to be painted. All right? So this is a frame where that painter's being painted. This is the local frame where that guy's being painted. And what you'll see in the lab is that they're stretched or shrunk or sort of pulled around to fit the frame you give them. So they start off as square images, but if they're given a little rectangle like this, they'll change their size. So you'll see Philip and Alex do all sorts of weird contortions. So, how do we actually make a painter or show a painter on the screen, which I would be showing you? So the way that you guys pull in a painter, you can define the name Philip to be a load painter. Then in quotes, we're going to put Philip. What load painter is, it's a function that goes off and gets a file. Okay, and load painter has a directory hard-coded into it that goes to the proper directory for us. So it's actually looking for a file that's called philip.pgm in the directory home sickp images. Okay, so when we do load painter, this part here and the .pgm is all hard-coded for us, so all we have to give it is the name of the file. If you look in the directory home sickp images, you'll see that we only actually have 3 images available for you guys to be looking at. One is Philip, which is the picture of Philip and Alex, and the dog and Philip. The second picture is the AD logo ripped off of the webpage. And the third image is a picture of the Golden Gate Bridge, which I went on to photo.net, which is all of, you can find all of Philip's pictures, which are the ones that we have hanging up all over our walls. He's put all of his photo CDs up on photo.net, so you can actually go and pull down pictures of his. So I pulled down a couple. Your problem set talks about how you guys can create more images if you guys want to pull in your own. So you can do painters where it's a picture of you, your cat, your dog, your girlfriend, your boyfriend, your car, whatever. Okay? So the problem set talks about how you can convert JPEG or GIF files over to these .pgms that we need for painters. So, this is what?
Black screen.
Actually, you can define a black screen. How do we define a black screen? Well, there are different ways to create painters. So you can define black to be, there is a procedure called number to painter. I draw it as an arrow, but it's actually a dash greater than sign. So number to painter of 0. Okay, so number to painter takes in a number and creates a painter that is all that one color. And the numbers vary from 0 to 255, where 0 is black and 255 is white. Okay, so you guys can define shades of gray. Woo! So then if you use black in this, you'll get, even I can do that. Okay, so that's not that exciting. But what you, huh? Sure. Yeah, well, anyways, I take everything too literally. So we could do a gray. on a number to painter of your favorite number between 0 and 255? 137. An excellent choice. No, 17 unfortunately would probably be too close to black to really show up a difference. 170, sure. 117, some grayscale in there. Okay, so that's one way that we have to define a painter. This is another way that we have to pull in a painter, is to get this load painter. And what load painter does is it makes a call from picture to painter. There are two other ways to create painters. One of those is a procedure to painter. So we have define shading to be a procedure to painter. And what this does is it takes, you have to pass it a procedure of two arguments, x and y, where x and y are the coordinates. Okay, so the frame, and those vary from 0 to 1. And we can do something with those. So if we were just to add x and y, what would shading produce? Well, these numbers would fall slightly above 0. All of them would, because x and y vary between 0 to 1. So the largest that we're going to get is 1. The smallest we'll get is 0. Okay, that's really close to the 0 scale of these colors, which means we're really not going to see any difference. Sorry, yes, the largest is 2, which is also very close to 0. Right? So in this case, we're going to get numbers varying from 0 to 2. We're going to get black to just a little less black. You're not going to see a bit of difference. So what we could do is we could introduce some sort of scaling factor to that. And you could multiply it by 50 or 128. So what's that going to produce?
It's going to be a picture in which the lower left-hand corner is white and the upper right-hand corner is reasonable gray. And the shading is go up parallel to the
You're close, except that you got the colors confused.
Oh, sorry.
You're going to vary from black up towards white, and this middle band is going to be in the grayscale. Okay, so it's going to vary its shading as it goes up that way.
And the variance is parallel to the as you move up the
Right, as we move up that way. Okay, so that's the third way. I promised you 4. And there's something called segments to painter. And segments to painter takes in a list of line segments, and then it will actually draw those line segments for you. So this is how you could define a painter that looked like, I'll say, your favorite letter. No reason why we might pick H in any case. You probably want to pick something that is pretty easy to draw with straight lines. What you'll see in the problem set is we've defined the mark of Zorro. Okay. Okay, so there's 4 ways that you guys can create primitive painters to be using in this problem set. So those are the 4 ways. And the problem set goes through these 4 ways for you. Okay, what I'd like to talk a little bit about is how we can transform our painters. So we talked about just basically taking the painter and repainting it. But what if we want to flip it around? What if we want to rotate it? How do we rotate painters? So what I'd like to do is be able to take my happy little stick person so let's have happy little stick person here. Very tall person. And happy little stick person is going to hold something in one hand, because otherwise We're not going to really be able to tell if we're flipping or we're rotating. And we're going to rotate happy little stick person by 180 degrees. Okay, so that's rotation. So let's say we want to define a procedure called rotate 180, and it's going to take a painter as an argument. Okay. Defined on the code in henderson.scheme, you'll find a procedure called transform painter. One caveat, you will also find transform painter defined in the book. And you will notice that the code looks slightly different. This is one of the exercises in the problem set, to look at the code that we have in our problem set versus the code in the book and to convince yourself that it actually does the same thing. It will do the same thing. So we're going to transform the painter, and the code that we have in hen.scheme takes three things as arguments to transform painter. The first thing it's going to take is a new origin vector. The second thing it's going to take is the new edge 1 vector. And the third thing will be the new edge 2. So in this case, here's our origin. And we're going to do this in the frame map coordinates. Here's our edge 1, 1, 0. And here's our edge 2, which is 0, 1. Well, what happens when we invert the little guy? Where's the origin now? All right, so here's the new origin. Where is edge 1?
0, 1.
And where is edge 2? Okay, so we transform the painter, and we have a constructor called makeVect. So we need to give the new origin vector, which is 1, 1. MakeVect 1, 1. The new edge 1. MakeVect of 0, 1. And then the new edge 2, makeVect on 1, 0. So that procedure, when past a painter, will rotate at 180 degrees. Now, what if I don't want to rotate, but instead what I'd like to do is flip it vertically? So here again, this happy little stick person. And this I'm going to actually have to look at because this is what we want here. So we flipped it vertically instead of rotating it. Where is the origin? Where is edge 1?
1, 1.
Edge 2? Hopefully coming out of the same origin. Okay, so how would we write? Define, we'll call this flip vert, which takes a painter. And we're going to call transform painter with our new origin, which is makeVect 0, 1. Our new edge 1, make vect 1, 1. And finally, our new edge 2, make vect of 0, 0. It doesn't take a painter as the argument, so neither should rotate. Okay. And why is this?
Transform painter already does.
Because transform painter does handle this on the painter. So basically, this is a bug between the book and our code. So basically, the version of transform painter that we're using in hen scheme returns a procedure that takes a painter. Okay, which is why we don't need to. The version that the book is using does not do that. It does not return a procedure. So that's what we need to actually. What the book does is it takes the painter and then passes that as the first of 4 arguments. Okay, so I actually crossed the code between the two, which is bad. Okay, so that's how it should be defined in our system. Okay, so that's flipping, that's rotating. We saw splitting, recursively splitting, yeah, but it's more. Okay, so what you're asking is why in 1 are we calling make vect 1 and 0, and why would we call that?
Yeah, why is
The reason, quite honestly, that it's different is I typed in flipvert out of the book, and the other code existed beforehand. In Scheme, these numbers are the same, right? Because Scheme doesn't differentiate between integers and floats. It doesn't care. So in fact,
In the book assumes that it does.
the book is assuming that it is. In our version, it doesn't.
Make a difference.
Then it would. Right. Right.
But it's not the list, you know, the dot, it's actually 1.0.
No. So it's going to be it's actually a number. And in fact, you can't write something like, if you want to make a console, you just can't write this.
Yeah, that's
You have to
why-
build a console by actually saying cons 3, 4. Okay, so we can't do that using the dot. If you do the quote. Right, but it wouldn't work here. You can't, if you use a quote, but you can't just say 1.0 and have that be a console. Right. It's okay. So, with that, since we don't have a projector, I think it would be better for us to get into the lab, start playing with this. If you guys do a meta X load problem set, you have to type in the 4. The default was still 3. I didn't want to change it this morning while you guys were doing it. So just make sure you type in that you want to load in the code for problem set 4 when you do the meta X load problem set. And we will go into the lab, and hopefully this will all be working. Everybody's graphics cards will be working. Otherwise, we'll all crowd around my laptop for the afternoon and work on this.